And this is section 2.7 for precalculus. And in this section, we want to look at solving polynomial and rational inequalities. Okay, so let's get down and look at the teaching notes here. So for solving polynomial inequalities, now first of all, when we say polynomial inequalities, this function f of x is a polynomial. So an inequality means not equals 0, but less than 0, or greater than 0, or less than or equal to 0, or greater than or equal to 0. So if you don't have it in one of those four forms, that's the first thing you have to do, is to manipulate your equation so you get it a 0 on the right-hand side, and then your sign of whatever it is, less than or whatever. So you want to express it either way, as f of x is less than 0 or f of x is greater than 0, and work with that. If it's equal to 0, then we'll just remember that at the end. So then solve f of x equals 0. These are what are called boundary points. If we want to know where it's equal to 0 because of less than or equal to 0 or greater than or equal to 0, then those boundary points would be included in my solution. If we have strictly less than or strictly greater than 0, then those boundary points would not be included in my solution. Then we locate those boundary points on a number line, thereby dividing the number line into intervals. And we choose a test value in each interval to evaluate the function. So we evaluate the function at a test value in each interval. And if f is positive, when we evaluate it at a test value, then it's positive for all x in that interval. If f is negative for a test value, then it's negative for all x in that interval. And then we write the solution set, selecting the intervals that satisfy the inequality. So for example, say we want to solve 9x squared minus 6x plus 1 is less than 0. The first thing we do is we set it equal to 0 to find our boundary points. Now we won't include these in our solution because we're solving strictly less than 0. So then I ask myself, well, that's a quadratic equation. Can I factor it? And if you play with that a little bit, you should be able to see that you can factor that into 3x minus 1 times 3x minus 1, or 3x minus 1 quantity squared equals 0, which means we only have one boundary point. X equals 1/3, right? 3x minus 1 equals 0 means x equals 1/3. So there's our boundary point. We will not include that in the solution, but I'm going to test that. I'm going to test it to the left of that boundary point and to the right. So a value that's easy to test to the left of that boundary point would be 0. I take x equals 0, I plug it into my function. When x is 0, I get 0 minus 0 plus 1. So 1 is greater than 0. So everywhere over here, the function is positive, between negative infinity all the way up to 1/3, not including 1/3. And then I test the value to the right of 1/3, which would be an easy one, would be x equals 1. You can choose any number, but choose the easiest one you can. So when I plug in x equals 1 into the function, I get 9 minus 6 is 3, plus 1 is 4, so 4 is positive. So that means everywhere from 1/3 to infinity, the function is positive. So wait a minute. I want to know where this function is less than 0. Well, it's positive here, and it's equal to 0 at 1/3. So there is no values of x for which that function is less than 0. So our solution would be what's called the null set or the empty set. There is no solution. All right, what about rational inequalities? How is this different? Well, now my function is not just a polynomial, but a rational function, which is a polynomial divided by a polynomial. And again, I'm looking at less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0. And the procedure is the same, except we have to add points where q of x equals 0 to the boundary points, because you can't have those in the solution, right? Q of x equals 0 means this is not even a defined function. So we can't have those in the solution either. So I have to worry about where it's equal to 0, and then also where the denominator itself is equal to 0. So where both p of x and q of x are equal to 0. So let's say I want to solve this rational inequality, right? I have a rational function, polynomial divided by polynomial. And I want to know where that's greater than or equal to 0. So I have to look at both the numerator and denominator, see where they're equal to 0 first, and those will be boundary points. So p of x is x minus 1 times x plus 2, set that equal to 0. That's my numerator. So that means that x equals 1 and x equals minus 2 would be boundary points. The denominator, q of x, is x minus 3, set that equal to 0. That means x equals 3. So x equals 3 is a boundary point. So now I'm putting the three boundary points, minus 2, 1, and 3. I'm putting them in order because I want a number line, okay? And then right above them, I'm writing the number 0 here and the number 0 here because those were where the numerator was 0. Above 3, which is where the denominator was 0, I'm writing undefined because the function itself is undefined there. But all three of those are boundary points. So now I have to check in each interval. So between minus infinity and minus 2, I need to pick a value that's pretty easy to plug into the function. So I'll pick minus 3. When I pick in x equals minus 3 and plug it in, I get minus 4 times minus 1 divided by minus 6. That's a minus 2/3, which is negative. So I'm going to put some little negative signs up here to say to myself that everywhere from minus infinity to minus 2, it's negative. At minus 2, it's 0. Now between minus 2 and 1, I'm going to pick a value that's easy to plug in. I probably pick x equals 0. So I pick x equals 0, plug it in, I get minus 1 times 2 over minus 3. I get 2/3, which is positive. So I'm going to put in little plus signs over here to indicate that between minus 2 and 1, the function is positive everywhere. Again, at 1, it's 0. So now between 1 and 3, I got to pick a value, a test value. I'll pick 2. Again, I'm picking an integer value that's easy to plug in. So when I plug in 2 into my function, right, 2 minus 1 is 1, times 2 plus 2 is 4, 1 times 4 over minus 1, so I get minus 4. That's a negative value, so I put little negative signs here. That tells me the function is negative between 1 and 3. After 3, pick an easy value. Let's pick 4. Plug in 4, I get 3 times 6 divided by 1. I get 18, which is positive, so everywhere here is positive. All right, so what did I want? I wanted greater than or equal to 0. So from minus infinity up to negative 2, not including negative 2 was negative, so we don't want there. But at negative 2, it becomes 0. And then between negative 2 and 1, it's positive. And then at 1, it's still 0. So negative 2 to 1, including both, means I put square brackets around them. Or notice from 3 out to infinity, it's still positive. But I can't include 3 because it's undefined there. So parentheses around 3. All right. As a third example in this section, we want to solve this absolute value inequality. That's still a polynomial inequality. It's just that I want the absolute value. So if the absolute value of a number is bigger than 3, that means that that number itself is bigger than 3, or that number is less than minus 3. So you actually have two polynomial inequalities to solve. Okay, two polynomial inequalities. So work on them one at a time. So x squared minus x plus 1 is greater than 3. Now you got to get it into a form where you have 0 on the right hand side. So subtract 3 from both sides. X squared minus x minus 2 is greater than 0. Remember, we got to get it in a form where I have something greater than 0. The function is greater than 0. So now I have this quadratic greater than 0. I want to figure out where it's equal to 0. So I have a quadratic equal to 0. That's going to be a boundary points. This is easily factorable also into x minus 2 times x plus 1 set equal to 0. That means x equals 2 and minus 1 are my boundary points. So I have a number line, so I'm going to plug in minus 1 and 2 on my number line, then I'm going to check in each interval. Okay? It's 0 at those points, and it's positive there, negative here, positive here with checking these points. I got to do the same thing for less than minus 3, so I add 3 to both sides. I get this quadratic less than 0. And I look at that for a while. I say I can't factor it, so I'm going to use the quadratic formula. When I use the quadratic formula, I actually see that there are no real boundary points. These are imaginary numbers, right? I got the square root of minus 15. So there are no real boundary points. So all I need to know is just pick any value, and it's always going to be that value everywhere. So since my boundaries are infinity, essentially minus infinity to infinity, I just check one point in there. Easiest one to check is 0. I see that that function then will always be positive. So there are no solutions to that function being negative. So the only solutions are over here, where this is positive and this is positive. So x is from minus infinity to minus 1, or 2 to infinity. So that is my solution. All right, we're going to use the same idea to find the domain of f of x equals 9x squared minus 4, the square root of that. So when you ask to find the domain of a function like this, what you need to think about is that everything under a square root has to be positive or 0. So essentially what I'm saying is what values of x make 9x squared minus 4 positive or zero, in other words, greater than or equal to zero. So that's what I want to solve, which is a polynomial inequality. So I go through the same steps. First thing I do is figure out where it's equal to zero for boundary points. I can see that that can be factored into 3x plus 2 times 3x minus 2, right? It's a difference of squares. Set that equal to 0. I see that x is minus 2/3 or x equals 2/3. So I put those on a number line. I see the function is 0 there, and then I have to check points in each interval. So I'm going to check -1, 0, and 1. I see I get those values, so it's positive from minus infinity up to minus 2/3 and from 2/3 to infinity. And I actually want to include those boundary points because I want greater than or equal to 0. So this then is the domain of that function because it led me to solve that polynomial inequality.